Welcome back, Science 10. This is the third installment of the CD3 booklet, 2.9, monitoring changes in population. So, take a look. It starts off here with something relatively interesting and somewhat scary in a way. The population of humans on the planet remained remarkably stable for thousands of years until the Industrial Revolution happened, invention of agriculture, etc. It seems like after that, it's skyrocketed. So for example here, if we look at the year 2000, just a little over 6 billion. Once we reach 2025, we'll be around 8.4 billion. And there's many things online you can look at too. For example, World Population Clock. The US population right now, as when this video was made, 320 million, and you can see it increase. Here's the population increase. So if you take births and deaths into account, you get a net increase. World population, at the time of this video was made, 7.2 billion. And even if you take deaths and births into consideration, there are far more births than deaths, and you can see it's just a motoring here. So world population, US population, you can see it's continually increasing, just like this graph is implying here. Okay. When a significant number of human societies switch from hunting and gathering to agriculture, the human population began to grow. Societies that harvest and store food for use during the winter months or during periods of drought have an advantage over those that must seek their food every day. During the centuries that followed the switch to agriculture, there was a steady rise in human population, but no real explosion. It wasn't until the mid-1600s that the global population reached about 500 million. During the last 3 decades, the global population has risen at an exponential rate. So curving upwards, that is an exponential rate, as opposed to a straight line in which we have a steady increase. It's really shooting up quick. That's an exponential rate. The population increased from 500 million in 1650 to 1 billion in 1850. The doubling took 200 years. The next doubling to 2 billion took only 80 years. From 1930 to 1975, which is 45 years, the population doubled again. So you can see it's doubling during a smaller time span, a smaller and smaller time span. And we're continuing to go at that rate. The current annual growth rate of 1.55%, which adds about 80 million people per year, the next doubling to 8 billion will be complete by 2013, only 39 years. Now this textbook was made earlier. We've surpassed 2013, and we're not quite at 8 billion yet, so we're not quite following that exact trend. We're at 7.2 billion. Okay, so it hasn't increased quite as drastically, but still, we are increasing. Population growth patterns. Changes in population size in a community occur when individuals are added or removed from a population, as seen in Table 1 here. So we have various factors here which come into play, 4 of them to be exact. Natality, which is birth rate, increases while other factors remain constant, the population will increase. So how many people are being born? The same holds true for immigration increases. The reverse effect occurs for mortality or death rate or emigration. So if we take a look here, natality is births, immigration is individuals moving into an area, so people who come from another country into Canada, that is immigration coming in. Mortality is death rate, people dying, of course you lose population there. Emigration, people leaving our country to go somewhere else, if we look at that, that of course decreases population as well. So natality and immigration increase the rate, whereas mortality and emigration decrease. In populations in natural ecosystems, all 4 of these interact. If we look at our planet as a whole, we just have natality and mortality, because as far as we know, we don't have any emigration into the planet and emigration out of the planet. Who knows though? With natality and mortality have the greatest effect in a natural ecosystem. The 4 factors involved in the population growth can be expressed mathematically. So if you want to figure out the population growth of an area, of course you add up the things that will increase a population, add up the things that decrease a population, and of course the increasing factors minus the decreasing factors will give you how much you need to add on or subtract from your current population to figure out what's going to happen. In mature ecosystems where resources tend to be constant or available in predictable patterns, populations remain relatively stable, so they have a zero population growth. Births are balanced by deaths, immigration is balanced by emigration, etc. Or births and immigration balanced by death and immigration. And of course we don't see that balance here. We see that we're constantly increasing if you look at humans as a whole. This balance is referred to as a dynamic equilibrium or a steady state. Okay, open and closed populations. Ecologists classify populations as either opened or closed. In most natural ecosystems, all four factors, natality, mortality, immigration, emigration, are acting on the population of each organism. These are said to be open populations. Species can come in, species can go out. However, immigration and emigration do not happen in laboratory settings or game reserves or zoos. I suppose that the emigration is controlled in zoos. So populations of organisms in these situations are closed, and only births and deaths affect population size. Okay? The global population of humans or any other of the organisms is also considered a closed population. People do not emigrate to other planets, and as far as we know, none are immigrating either. Changes in the size of a global population result from only births and deaths, natality and mortality. The current rate of global human population is about 2 times as many births as deaths, which means that in 1996, Earth's population of 5.8 billion increased by 89.9 million people, or by 246,200 people each day. That's almost the population of Regina. So if you imagine it, at the end of each day, okay, we have that many more people on the planet, and that's quite amazing. It's quite difficult to fathom that much. So we have this many more people per day on the planet. It's like a population of Regina, just coming out of nothing. The human population is not in a dynamic equilibrium. Okay, next thing we look at are these population histograms, which are graphs. So we see the left side here is male, right side female, age group of people, so babies, young kids, teenagers, adults, young adults, middle-aged adults, and then older people, etc., giving you the dispersion of how many are each category. So if we look at population histograms, they're useful when studying populations of long-lived organisms such as humans. Double histograms are often used to provide a profile of age group by sex. These histograms allow you to examine populations of an organism in terms of its age and proportions of males and females at a specific time. The shape of the pyramid allows you to predict the changes in the population. A pyramid with a wide base, such as here, so a wider base, of course that illustrates that there's a lot of young people there. So, and if there are a lot of young people, it's a growing population. It means that the number of births has been high recently. Another indicator of future growth is the number of individuals capable of reproduction. If the number is high, it means that a large number of births can be expected in coming years. In a human population, individuals of a reproductive age would be found at the center of the pyramid. So Mexico, for example, would illustrate a growing population because you have many, many, many young people. Okay, so a wide base indicates a growing population. In contrast, histogram B here, so the one that's kind of up here, or the one here where it's mentioning Sweden in 1997, represents a stable population. So there are fewer births and deaths than in the other one. In addition, with infant mortality rates, the mortality of most other age groups, the population is growing slowly. So you can see it's almost stable as you go up. It's not too far, it's a little bit jagged, but the population is relatively the same as you go up. This population is approaching what is described as zero growth, so it's going to remain relatively the same. When the base of the pyramid is narrower, so here you can kind of see it's narrower here, where the most people are in this region here, or if you look at this Canadian one in 1997, it's there too. So it shows a population actually decline. Okay, Now the word here got scratched off here, but it says shows population histograms for 3 countries. So in the base is narrower, fewer offsprings are produced. So if this trend continues, in which we have fewer people being born, we will experience a decline in that population. Okay, so the 3 general shapes there: growing population, stable population, declining population, if those trends continue. Okay, so that's it. We'll look at what questions I'd like you to do. I'd like you to do number 1 here. In your own words, explain the difference between populations with a linear growth versus exponential. Linear is a straight line increase like this, whereas exponential is curving upwards, just like was mentioned here with the world population graph. Okay, provide an example of your answer. What type of growth pattern is the human population undergoing right now? Explain your answer. 4 factors regulate population growth. Use an example of a non-human population to explain how each factor affects the population size. Okay, so those 4 factors that were mentioned earlier. 4, in your own words, explain the difference between open and closed populations and give an example. Give 2 examples of each. Here, draw a population histogram that represents a population with declining growth rate. Now you can just sketch that. It looks something like one of these. You have to remember which one I talked about, which represents a declining one, in order to answer that question, and explain why the population will decline. 6 refers to this graph over here. It has a paramecium, a single-celled living organism, and something that it feeds on, algae. Paramecia feed on algae, so it's in a pond. As the pond slowly warms, more algae grow. Okay, and we can see that since paramecium eat algae, they're going to grow too, but look at how they're growing though. They're not growing at the same rate. As the pond slowly warms, more algae grows. To answer these questions, use the graph. So explain why the paramecium population is increasing. Which population provides an example of linear growth? Explain your answer. Predict what might happen to the population of algae and paramecium after this point here, at point B. So what could happen after this point? And then I don't think I'll make you do B here. We'll just stop at that, and you can finish off with C. This last question though, 7, in 1999 the population of varying hares, rabbits in a mixed woodland system was 60. So they start off with 60. During 1999, the following data was obtained at the end of the year. So you have births, immigration, deaths, emigration. Calculate the population that would happen at the end. So of course we use this little relationship here that we talked about earlier, the population growth equation there, and you can figure out what happens there, what the population will become. Okay, to figure out the population growth as a percentage, you would take how many more hares there are at the end of the year, divide by 60 times 100. Okay, so whatever you get here, whatever you're going to add on to 60, you do for A to figure out the total population, but to figure out the growth percent, you take the number of increased or decreased divided by 60 times 100. Okay, so there you have it. We'll see you again.